Dear students, in this video, I am going to explain about lesson number 2, quantum mechanical model of atom, topic number 3, wave-particle duality of matter. According to Albert Einstein, light has dual character. What are the two different characters possessed by light? One is particle character and another one is wave character. So Albert Einstein was the first person who find the dual nature present in light. It means the light can travel in the form of particle and it can also travel in the form of wave. Look at the second diagram. Here the light is traveling in the form of particles. And look at the first diagram. Here the light is traveling in the form of the wave. So these are the two important natures that the light has possessed. It was identified by the scientist called Albert Einstein. So Albert Einstein found the dual character present in light. Okay. Now after Albert Einstein, the next scientist called Louis D Broglie, he extended the idea of Einstein to all the subatomic particles and all the microscopic particles. So Albert Einstein, he proposed the dual nature only for light, but D Broglie found that not only light, all the subatomic particle and all the microscopic particle have the dual nature. This was found by Louis D Broglie. So he tried to bring about the relationship between the particle and the wave character by his relationship called the D Broglie relation. Now let us see how the D Broglie relates the particle character and the wave character into a combined form of the equation. Now the first expression, E is equal to h nu. What does it says? E is equal to h nu means here E is nothing but energy of the photon. Now we are going to consider the energy for the photon. Photon means light. Okay, light. The energy of the photon having wave character. Now I am going to assume that light is going to have wave character alone. If the light is having wave character, its energy, okay, the light is coming now in the form of wave. The energy of the light, that is the energy of the photon, is given by the equation E is equal to h into nu. H means Planck's constant. Nu is the frequency of the radiation. So this is the expression that gives the wave character for light. Similarly, look at the second equation. Here the energy of the photon is represented in the form of the particle character. Suppose if the light is traveling in the form of particle character, then its energy will be as E is equal to mc square. Here m is the mass of the light, mass of the photon, and c is the velocity of the photon. So we have two expressions. One is the wave character, energy of photon in terms of wave character, and the second one is energy of photon in terms of particle character. Now what we are going to do, we are going to combine equation 1 and 2. So I will be getting h nu is equal to mc square. H nu is equal to mc square. We already know nu is equal to c by lambda. Now I am going to substitute nu in terms of, instead of nu, I am going to substitute c by lambda. So what I will be getting, h into c by lambda is equal to mc square. So just by keeping the lambda on one side, bring the hc on the other side. So hc by mc square, cc will get cancelled. So for the final expression will be lambda is equal to h by mc. So here this third equation, that is lambda is equal to h by mc, is represents the wavelength of photons whose momentum is given by m into c. Momentum means mass into velocity. So here m is the mass of the photon and c is the velocity of the photon. So here the photons have zero rest mass. We know very well the light will travel from one point to another point without any rest. But light on பண்ணிட்டோம் அப்படின்னா ஒரு இடத்துல இன்னொரு இடத்துக்கு அப்படியே ட்ராவல் ஆகி போய்கிட்டே இருக்கும். It will not find any rest at any point. So it does not have zero rest mass. So this is the meaning. So I have found the expression for wavelength of the photon. Now come to the next one. Here lambda is equal to h by mv. In previous equation lambda is equal to h by mc. Here it is converted as lambda is equal to h by mv. What is the difference between the third equation and fourth equation? Third equation represents the wavelength for photon, and fourth equation represents the wavelength for all the material particle. Not only photon, the fourth equation represents the wavelength for all the material particle, which means proton, neutron, electron, other subatomic particle, even a piece of chalk piece, whatever the substances we find in and around us, whether it is microscopic or macroscopic, we can apply with this equation. Okay, so this equation is valid only when the particle travels at the speed much less than the speed of light. The fourth equation will get valid only when the particle travels with the speed less than that of the light. Okay, so this equation shows that the moving particle is considered as a wave. Okay, and the wave can exhibit the property of the momentum. So for a particle with high linear momentum, what is meant by the word high linear momentum? High linear means இப்போ ஒரு ஆப்ஜெக்டோடைய மாஸ் அதிகமாக இருக்குது. ஓகே, ஸோ the object size and mass are high means it will not form a very high wavelength. வேவ்லென்த்தோட ஆம்ப்ளிடியூட் வந்து ரொம்ப கம்மியாக இருக்கும். ஓகே, அதே இது ஒரு ஆப்ஜெக்ட் ரொம்ப சின்ன ஆப்ஜெக்டாக இருக்குது அப்படின்னா இட் கேன் ஏபிள் டு ஃபார்ம் எ வெரி குட் வேவ் வித் வெரி குட் ஆம்ப்ளிடியூட். ஓகே, அப்போ ஹியர் ஹை லீனியர் மொமெண்டம். அப்போ லீனியர் மீன்ஸ் தேர் த வேவ்லென்த் இஸ் very very small. Wavelength is very very small. Okay, and if low linear or less linear momentum means the wavelength will be very very high. Okay, for a microscopic particle such as electron, the mass is in the order of 10 power minus 31 kilogram. Hence the wavelength will be very very larger and than the size of the atom and become significant. Since the electrons are microscopic in nature, ரொம்ப tiny shapeல இருக்கறனால wavelength will be very very larger and it becomes significant. For example, instead of electron, let us assume a stone moving in the form of wave. Stone means it will have certain mass and weight, so its velocity will be very very slow when compared to that of the microscopic particle electron, and it will show a very small wavelength, or it is called as a linear momentum, high linear momentum. Okay, next let us explain the dual matter with the help of the equation, with the help of an example problem. Let us understand this by calculating D Broglie wavelength in two cases. First case, a 6.626 kilogram of iron ball moving with 10 meter per second. Second case, an electron moving at 72.73 meter per second. So among these two, which one obeys the wave particle duality of matter? That is what we are going to see. So first let us take the first example. The wavelength for iron ball is equal to h by mv. H value, h means Planck's constant, which is nothing but 6.626 into 10 power minus 34 kilogram meter square per second, divided by m, mass into velocity. Already it is given in the question, 6.626 kilogram into 10 meter per second. So upon substituting these things, we will and on simplification we will be getting the answer is 1 into 10 power minus 35. 1 into 10 power minus 35. This is the wavelength for the iron ball having mass of 6.626 kilogram. Now let us come to the second example. Electron moving with 72.73 meter per second. The same formula only. Upon substituting all the value, finally I am getting the answer as 1 into 10 power 5 meter. It is given in the old book. So we have to change it as 1 into 10 power minus 5 meter. Okay, in old book it is given as 10 power 5. If you are using old book, change it as 10 power minus 5. If it is a new book, no problem. Okay, so we have received two answers, 1 into 10 power minus 5 for electron and 1 into 10 power minus 35 meter for iron ball. So among these two, which is very very small? Which wavelength is very very small? 1 into 10 power minus 5 is very very small. So the 1 into 10 power minus 35 is very small when compared to 1 into 10 power minus 5. Okay, அப்போ 1 into 10 power minus 35 means there the wavelength is very 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 small. It shows high linear momentum. 1 into 10 power minus 5 for electron means there the wavelength is larger when compared to that of the wavelength of the iron ball. Okay, so here iron ball being larger in size, it shows very small wavelength, that is it shows high linear momentum. What about electron being microscopic in nature? It shows a very good wavelength with very good amplitude, so it is little bit significant in nature. So this equation, the wave particle duality, that is the D Broglie equation, is applicable only for microscopic particle and not for the macroscopic particle. So these are something about the wave particle duality of matter. Thank you.